Every text message, every YouTube video, every email, every Wi-Fi connection. Although they seem completely different, they all have one thing in common. They are transmitted as digital data. But how can billions of zeros and ones travel through the air as radio waves? In the previous lessons, we explored analog communication through AM and FM systems. These systems transmit continuously varying signals that directly represent information such as voice or music. While analog communication is simple and effective, modern communication systems face much greater demands. Today's networks must carry high-definition video, internet traffic, cloud data, GPS information, and billions of smartphone messages simultaneously. Analog communication alone cannot efficiently support these enormous data requirements. This raises an important engineering question. Instead of transmitting continuously varying signals, can we represent information using only two simple values, 0 and 1? The answer forms the foundation of digital communication. Digital communication is the process of transmitting information by representing it as a sequence of discrete binary digits, called bits. Unlike analog communication, where signals change continuously, digital communication converts information into combinations of zeros and ones. These bits are processed, encoded, modulated, transmitted, received, and finally reconstructed into the original information. The overall process usually follows these steps. Information bits digital modulation, communication channel demodulation, bits reconstructed information. Although the physical transmission still occurs using analog electromagnetic waves, the information itself is represented digitally. Intuitively, imagine writing a book using only two symbols instead of thousands of different characters. At first, this seems impossible, but by arranging the two symbols into different combinations, every word, sentence, and idea can still be represented. Digital communication works exactly the same way, using only zeros and ones. Physically, consider sending a photograph through a smartphone. The camera first converts the image into millions of binary bits. These bits are compressed, encoded, and mapped onto an RF carrier using digital modulation. After traveling through the communication channel, the receiver detects the transmitted symbols, reconstructs the original bit stream, and recreates the photograph almost perfectly. Mathematically, digital communication represents information using discrete binary symbols rather than continuously varying waveforms. These symbols are processed by digital circuits before being converted into analog RF signals for wireless transmission. Digital communication is the foundation of nearly every modern wireless technology. Wi-Fi, Bluetooth, LTE, 5G, satellite internet, GPS, IoT devices, and fiber optic networks all rely on digital communication techniques. Digital systems offer many important advantages. They provide excellent noise immunity, support error detection and correction, enable encryption and data compression, achieve higher spectral efficiency, and integrate naturally with computers and digital processors. For RF engineers, digital communication combines two worlds. Digital processors generate and manipulate binary information, while analog RF circuits transmit and receive the corresponding electromagnetic signals. Successful system design requires understanding both domains. Digital communication has transformed modern society by making reliable, high-speed global communication possible. Nearly every wireless technology we use today depends on converting information into binary data before transmission. A common misconception is that digital communication means radio waves themselves become digital. In reality, electromagnetic waves are always analog. What becomes digital is the information carried by those waves. RF hardware still generates continuous analog signals, while the transmitted data is represented digitally. Now that we understand the basic concept of digital communication, the next step is to see how binary data becomes a physical signal. In the next lesson, we will explore bit-to-signal conversion and discover how zeros and ones are transformed into waveforms that can be transmitted through a communication channel. In this lesson, we learned that digital communication represents information using binary bits instead of continuously varying analog signals. We also saw how modern communication systems convert information into bits before transmitting it over analog electromagnetic waves. In the next lesson, we will explore bit-to-signal conversion and discover how digital bits are transformed into physical signals for transmission. If you found this useful, like the video, subscribe, and follow for the next lesson.